Hi, hello there. Good afternoon, good morning, wherever you are logging into this virtual summit at Spark AI. This year, to start off with, I want to acknowledge everyone's presence here. It's a very crazy world out there, and I realize things have not been as normal as we would have liked. But then again, this is the world we are living in. So thank you all for joining in today. For this session today, we will be talking about my work and my team's work around clinical suspecting and some of the issues that we had to resolve along the way while working with PySpark. And that is kind of what I will try to give away with this session is not try to talk too much about PySpark as is. I'm pretty sure most of the participants would have worked in some capacity or the other with Python, PySpark or Spark environment. Uh, so let's start off and try to understand what machine learning use case we are trying to solve and what were the problems we faced and how did we solve it. So, brief introduction about myself for those of you who are joining and who don't entirely are aware of me or the company. So, I am currently heading machine learning at Episource as a vice president there. Episource is a healthcare company based in US, and we work extensively with insurance companies and hospitals to allow for risk adjustment and provide services around healthcare in US. And my team majorly works on NLP and machine learning platforms, and we focus on building machine learning platforms at scale. For example, one of the engines and the platforms that we had built last year processed more than 100 million pages in the financial year last year. And personally, I belong with academic training. I belong to pure sciences and maths, and I am a self-taught programmer. I've picked up a few programming languages along the way. I'm also a trained AWS Solutions Architect certified, and I worked in my previous roles and companies. I worked in deploying machine learning, analytics, and artificial intelligence-based solutions in multiple domains. And overall, I love Python. I love numbers, and I really love building anything that I can get my hands on. So for today, let's kind of try to walk through a few of the key elements of the use case around machine learning that we are trying to build out, and along with trying to understand what were the issues and with PySpark and how did we go about resolving it. And since if it would have been in person, I would have taken a very different approach to this presentation. But I realized that there would be a lot of follow-up questions in a virtual format. Hence, I tried to keep it as straightforward as possible and giving as and trying to condense as much information as possible within the provided time. So we'll just do broadly focus on four key areas. What was the broad use case that we were trying to solve, the problem statement itself. We try to understand what was the data profile of the machine learning problem statement that we're calling clinical suspecting here, and what does clinical suspecting even mean, and try to understand that at the very outset. And we'll kind of also try to understand why did we go about using Spark, and also what were the issues around it, and how did we kind of resolve it. So let's get started with that. And when we're talking about clinical suspecting, the broad use case at this point in time for when we say clinical suspecting is, if I have to put it in one sentence, it is essentially looking at some key variables predict whether or not a person will have a disease. For example, I have to look at a patient's profile, the medicines that he has had, his parents' medical history, the lab tests that he has been tested on, the procedures if he has had any comorbidities that if he has, and any patient visit history with his previous doctors, and take all of that into account and say, okay, hey, I have all of this information, and does this person suffer from a certain disease? Now, of course, as the clinical domain or the healthcare domain goes, there's not only one disease. There are literally hundreds of diseases out there. But for our problem statement, we chose around 80 odd diseases only. So what that meant was it was a classification problem, of course, where we have a lot of independent variables broadly fitting into these five categories as I am showcasing. But it also means that it is a multi-class, multi-label problem, which means the same person could have one or more diseases himself. So this person could be suffering from diabetes and hypertension. This person could be suffering from diabetes, hypertension, and a chronic kidney problem, which meant that the prediction, the feature engineering, as well as the data logic becomes very complicated. So with that, kind of let's try to also understand why did we choose Spark. Now we had data for patients for over 4 years, and we try to kind of profile it for over 1.2 million patients, of course, over 4 years. And this data was spread across the five broad categories that I just mentioned earlier around comorbidities, around the patient's visit history, the lab tests, the procedures that have been performed on him. And there were over 25,000 features. This is without any feature engineering, which meant that there were a lot of columns that we had to work with. It was 500 GBs of raw data just for these 1.2 million patients, which meant that, of course, we could not use the normal Pythonic methods that we could use to do machine learning in Scikit or Keras or TensorFlow out there. So the broad process flow for doing machine learning for this use case was something like this. Okay, this is a very 30,000 feet view out there. That's not as detailed as I would have liked to present, but there's just a very broad view of what is out there. So we first, of course, have to load the data. We have to clean it based on some logic, which is dependent on some of the business logics that we have to write up. For example, if someone has diabetes, then I don't want to capture both of the type of diabetes. If the person suffers from diabetes type 1 or type 2, then I don't want to capture the other. So and of course, there were problems around the data sparsity. How do you logically group a person based on his gender, based on his location, based on his zip code, based on what lab test has he had in the previous time? And of course, then join all of these data across all the multiple categories, and then finally arrive at the data that you want to run any kind of machine learning on. And then, of course, I have 25,000 plus features and plus some more after doing feature engineering, which of course means that I cannot use everything. So I have to run feature importance pipelines based on a random forest based feature importance identifier, choose maybe top 5,000 features, convert them to sparse matrices, and then run a very straightforward multi-layer perceptron kind of architecture based on libraries like Keras or PyTorch or TensorFlow. And then, of course, we have to monitor how the training is going. So we have to monitor that on TensorBoard as well. So this is how the broad workflow of us working with the data went about, which of course means that we had to have had faced problems in each of these areas. And there were literally tons of problems that we faced because this was literally first time where we were doing any kind of training as well as trying to predict on a data at this scale. And which meant we realized on the outgo that we needed to get away from pandas, the normal scikit methods, and use something like a distributed machine learning on PySpark with on the cloud. And that essentially brings us to what were the issues that we faced. So as I mentioned that there were a lot of issues that we had to face and try to resolve within this period. And there were obvious problems at the very outset. There were problems around cloud computing. There were problems around data. There were problems around how do I ingest my data into a certain ML pipeline, because I also need to take snapshots to do some amount of exploratory analysis on my data. And even to do exploratory analysis, I cannot use pandas because I need to use all the data for all of my expertise analysis as well. So what I've done is I've shortlisted the top five problems which in a way took the most of our time debugging, as well as trying to find out ways around it, which also took a fair amount of research and took a fair amount of reaching out to people to try to resolve it and share it with you folks and see if that also helps you as well. So uh, the first issue at the very outset, of course, is as I mentioned, will come about when I'm loading the data. And of course, if I'm using pandas or a pandas plus ray kind of a technical stack, rays is of course something which allows you to work with large data frames. But even with using ray or even pandas alone, we used to often run with out of memory errors, and the dot apply and the dot map apply map kind of functions in pandas were very slow because we had a lot of complex business logic that we had to use, which required group by, which required fair amount of filtering, custom lambda functions, which was fairly slow with pandas. So then that is when we kind of took a decision to move to cloud and using Spark. For us, the stack that we used with working and deploying the machine learning model was using PySpark along with AWS EMR, which is the platform where we worked with Spark on AWS Cloud with Jupyter Lab, and of course using Jupyter Spot instances in the cluster to reduce the cost. Uh, and what we found is that a method of using the apply and the map functions was using UDFs, the user-defined functions in Spark. But even after doing all of that, what we found was that UDFs were still slow, though they were faster than pandas, but they were still slow. So, so this was the first problem that we faced with using PySpark. And how did we kind of go about resolving it? It was kind of essentially focusing on understanding why were the UDF slow. Why was my PySpark data frame processing my data in a slow manner? So that is when we realized that the data that we had was in zipped CSV format. It was compressed CSV, but we realized that when we are working with CSVs in Spark and especially with PySpark in a cloud environment, it really does not unlock all of the potential of PySpark that we can use. And that is where we realize that maybe there are some other data structures out there which can help us. And upon a lot of inquiring on Stack Overflow, reading a lot of blogs, trying and testing with multiple data formats, we arrived at the Parquet data format. And that was the fastest data format for us, for our use case, because we had lots of columns, we had lots of data as well. And Parquet allowed us to create the columnar data structure that Parquet is very famous for, and allow us to improve the speed of our UDFs, UDF functions, as well as allow us the improved speed that we were looking for the exploratory analysis that we wanted to do with data at the first scope. And so what we did essentially was we had an intermediate batch job which we wrote up to load these CSV files and dump it into Parquet formats. And any of these Spark jobs that we had to write will use these Parquet files rather than the CSV files. And this gave us immediate 10x speed up with the apply kind of style PySpark grammar. And it was tremendous improvement in the speeds of the exploratory analysis that we wanted to do, any of the data cleaning that we wanted to do, any business logic uh, testing that we wanted to do on the data, and it improved dramatically. And of course, it improved the joins, which we'll talk about in a while. So the second issue that we faced as we went along was again still with loading the data. Now this was the first issue which we had resolved, and we still found that okay, hey, UDFs are running fast, faster than pandas, more faster after we converted it to Parquet format, but it was still slow compared to what we had expected. We cannot still be running an EDA job which runs for 1 hour or 2 hours. I would ideally want that to be finished within 15 minutes at tops. And we still realized that UDFs were still running slow. And again, then this started another round of research and started another round of things where we had to go out and reach multiple people and ask them what was the major issue with this. And that is when we realized that uh, PySpark as a whole and the ecosystem that we were trying to build, we were using the data frames, but we were not defining the schema of the data frame for each of those columns with the exact data types. And that is what was tripping us up because now PySpark was spending a fair amount of time inferring the data type of each of the columns and then loading up them up in a data frame before executing any functions that we wanted it to work with. Now, especially with the amount of columns that we had, it was pretty noticeable. Had we had only maybe 10 or 15 columns, the performance difference would not have been noticeable. But since we had such a wide data frame to work with, the performance was very, very noticeable. And so what we did was try to define the exact data type of each of the data frames that we wanted to work with, depending on the category, depending on the joins that we were making. And that improved the speed again tremendously. And this was an additional 3x speed upon the 10x speed that we had reported earlier. And this was something which was very good for us because we realized that we had to work with data frames and define proper schema for each of them. But we also realized that it means that I cannot do that for 25,000 columns, and most of them were empty or had a lot of null values. So we had to be very selective about which columns to be using and how to be choosing them, and also be very rigid and strict in cleaning the data. Earlier, we could have tried to do feature importance on all of the columns, but now we realize that rather than trying to do that, I just be very strict in removing the columns which are not going to add much information, because that is also going to add time to my processing, because I also have to define the data type. And for that, we had to, of course, write up a lot of custom functions to define these data frame column data types on the code. And that kind of, in a way, was before we encountered the third issue, which was another major one. Is now we had cleaned up all the data, we had done exploit analysis on the data, we broadly knew which were the columns that we were going to use, and we were broadly aware of how these columns are going to be used. And of course, if I have to run any machine learning model, then I have to go out and join and use all of the features that I wanted. And that is where we encountered the issue with joining the data. Now, I have 5 broad categories of data, each of them which have been converted to Parquet, each of them which have been cleaned up, which each of them where the data frame types have been defined. And now when we're trying to join it, it was again very, very painfully slow, where each of those joins were taking anywhere up to 3 to 5 hours to join, which was ridiculous. And that was leading to multiple timeouts, multiple retries, and we had to do multiple instances of vertical scaling, where if I was working with, say, a 64 gig RAM machine, and if I wanted it to speed up, then I eventually would end up with a machine which is like of a 256 gig RAM, which is again ridiculous, because I could pretty sure add some more optimizations to my processing pipeline with PySpark and work with it. And the way we approached this and tried to resolve this was, we realized that Spark hates wide data frames, right? If I am working with, say, 2 data frames and trying to join them in Spark, each of them, say, having 10 columns or 20 columns, then it will do it without any complaint, and it'll do it very, very smoothly. But the moment each of those contain 1,000 columns or 2,000 columns or 3,000 columns, performance starts to degrade massively. And we did an internal exercise where we tried to see plot this drop-off point as where does the performance really start to degrade at which column uh, number in a way. And the reason why we did that analysis was to also give us some indication of how many columns can I really work with in my current scenario, and to give me a realistic time frame. Uh, and we realized that the performance slowly started degrading around 250 to 350 number of columns, and that was kind of a big realization because each of the data that we're working with, even after cleaning, had close to 2 to 3 thousand columns, and we cannot suddenly work with 250 or 300 columns only. And what we then did was we realized that there were a lot of irrelevant columns which we're still working with, and we ended up dropping all of them. A lot of them were information about, say, a patient's first name, patient's last name, those kind of columns, which we ended up dropping without even thinking. We also talked to our domain experts to realize which are the usual columns which would add more value to a machine learning model for this use case. And accordingly, we also chose the broad themes of columns that we had to work with. So what we did was we had this large data frame for each of those categories, and we broke it up into sub data frames. So we had close to five large data frames, and we ended up breaking each of them into five again. So we ended up with roughly 25 to 30 data frames overall, and each of them were themes. Like one of them would just focus on your lab tests done on your chest area. One of them would focus on procedures done which are invasive procedures. Another would be procedures which require you to get admitted to an hospital, and so on. So we created such theme data frames, and then we joined them based on our requirements. And this improved our speed of joins and speed of analysis and training massively. And what we realized that we had to be less greedy and limit the number of joins that we were trying to do at each point in time, and that was very helpful. And after cleaning the data, after loading the data, and solving all these problems around data, we now arrived at the problems around the training. And we realized that while we're training the data using the inbuilt Spark MLlib platform, the simple logistic regression or a random forest algorithm, and we realized that we were working with the dense matrices, and our features were defined in a way where we were feeding in multiple columns to work with. And that's something that we realized was pretty slow, and we didn't want to continue with that. And we realized that it was also impacting my choice of batch sizes. I could not work with very large batch sizes, and the number of iterations that I had to do before I realized that this is something that is going to be helpful for me. And it was also affecting whenever I was trying to, we were trying to do any kind of hyperparameter optimization exercise. Because now each of the hyperparameter optimization, while you're trying to explore the hyperparameter space, is going to take a huge amount of time. And that's where we came up with the solution for this. And we realized that we had to now convert these dense matrices to sparse matrices. And the obvious answer to that was using the vector assembler class in PySpark. Now, what vector assembler does is it takes in a list of columns which you want to use as features and converts them into a sparse representation. And of course, it infers what kind of representation would be the best for you. It may be sparse, it may be dense, but most of the time it ends up giving you a sparse representation. And of course, it takes that call based on the RAM, based on the amount of data, based on the requirements that you have. But if you want to be more explicit in defining those sparse representations, you could use something like a sparse vector or a vector UDT class in PySpark itself. But again, once you have created these, what we did was once we had created these sparse matrices, we just dumped them into Parquet feature files, which allowed us to train further using any algorithm or any framework like TensorFlow or PyTorch. to work with. And now, once this was solved, now then there was another final problem in a way, where we realized that okay, hey, this is a multi-class, multi-label classification problem, which means at any point in time, I'm trying to predict 80 classes together, and one patient may have a single disease, he may have 10 diseases, and which meant that my decision boundaries that were being created for those 80 classes is of course going to be very confused in a way, because there are a lot of the diseases which are supposed rare in a way, very rare hereditary genetic diseases, which you are not going to find in everyone, but something like a lifestyle disease like a hypertension or a diabetes, you're going to find it very easily in the population, which meant that my predictions for the popular diseases per se was very good, but for the rare genetic diseases, it was not as good as I would have liked. So what we realized that since this is a multi-class, multi-label problem, and I was not doing a good job of predicting these rare categories of diseases, I need to kind of improve my prediction methods. And of course, we were running multiple jobs with spot instances, trying to reduce the cost, but trying to predict so many classes out there was not very helpful. And of course, the problem was that we were running with the same set of features for all the categories. We were saying that, okay, hey, these are the set of features that I'll use to predict the popular diseases. I'll use the same set of features to predict my rare diseases, which is not uh, correct from a machine learning point of view, which meant that I had to do custom machine learning and feature engineering for each of these categories. And that is what we exactly did. And we realized that if I have to solve this issue, then I have to approach it from a very different way. And the way for it is to kind of do custom feature generation for each category. As I mentioned that I was treating the popular and the rare diseases together. The best way to do it is to treat them separately, have separate feature engineering pipelines and custom features for the rare ones, slightly different ones for the more popular, or the ones which have more incidence in your data, and then have individual binary classification models running on each category. So from one model which was trying to predict 80 categories, we then arrived at 80 models predicting 80 categories. And then the final classification was then a summation of all of these 80 models. And the classification was based on custom uh, logic, which we had to write to identify the top n categories, because of course there are comorbidities and dependencies that if the person has diabetes, then the chances of him having hypertension or diabetes related comorbidities is higher, which meant that I had to do custom probability enhancement for if a person has diabetes, and then there is a certain percentage chance that this person has a comorbid condition as well. So we had to write a custom category logic based on which we identify the top n categories. And to do all of this at a scale, we ended up writing Terraform and Boto 3 scripts to launch EMR multiple clusters for each of these categories. So at any point in time, I could just launch 80 EMR clusters, and which would just do all of the hyperparameter optimization for each of that model, and then dump the final model and the outputs into an AWS S3 bucket where we would store the outcomes. So this in a way is our the broad. I walked you through the broad problem statement that we had. What was the broad data profile? Why did we choose Spark? And what were the issues that we faced with Spark? And how did we solve it? So if I have to summarize the talk and the session here, I would essentially say the best practices for ML on Spark. And again, with the caveat, if it fits the use case that we had tried to resolve, then these would be my best practice summary. Of course, use Parquet formats. Don't use CSV or text file formats if you're working with Spark. Use narrow data frames. Spark hates wide data frames. Try to be less greedy. Try to reduce the number of joins. define a schema for your data frames, try to understand what data types you're working with, and try to resolve the data to the best possible format for that. And of course, before your training, use sparse matrices. There are some use cases where it does give reduced performance compared to dense matrices, but it broadly it works as good as dense, and it reduces your requirement for RAM and headache around managing in the infrastructure for machine learning massively. And of course, if you are encountered with a multi-class, multi-label problem, like the one that we had, it is almost always advised that you choose a hierarchical style classification using the binary classification approach that I just briefly talked about, and which would of course require doing custom feature engineering based on each categories that we work with. And so that would kind of be mostly be the end of my session. You can of course reach out to me on my email if you have follow-up questions. Connect with me on Twitter, and now I'm open to taking questions from you.